The Moon is Earth's only permanent natural satellite. It is one of the largest natural satellites in the Solar System, and the largest among planetary satellites relative to the size of the planet that it orbits. It is the second-densest satellite among those whose densities are known. The Moon is thought to have formed approximately 4.5 billion years ago, not long after Earth. There are several hypotheses for its origin. The most widely accepted explanation is that the Moon formed from the debris left over after a giant impact between Earth and a Mars-sized body called Theia. The Moon is in synchronous rotation with Earth, always showing the same face, with its near side marked by dark volcanic maria that fill the spaces between the bright ancient crustal highlands and the prominent impact craters. It is the second brightest regularly visible celestial object in Earth's sky after the Sun, as measured by luminance on Earth's surface. Its surface is actually dark with a reflectance just slightly higher than that of worn asphalt. Its prominence in the sky and its regular cycle of phases have made the Moon an important cultural influence since ancient times on language, calendars, art, and mythology. The Moon's gravitational influence produces the ocean tides, body tides, and the slight lengthening of the day. The Moon's current orbital distance is about 30 times the diameter of Earth, with its apparent size in the sky almost the same as that of the Sun, resulting in the Moon covering the Sun nearly precisely in total solar eclipse. This matching of apparent visual sight will not continue in the far future. The Moon's linear distance from Earth is currently increasing at a rate of 3.82 plus or minus 0.07 centimeters per year, but this rate is not constant. The Soviet Union's lunar program was the first to reach the Moon with unmanned spacecraft in 1959. The United States' NASA Apollo program achieved the only manned missions to date, beginning with the first manned lunar orbiting mission by Apollo 8 in 1968, and 6 manned lunar landings between 1969 and 1972, with the first being Apollo 11. These missions returned over 380 kilograms of lunar rocks, which have been used to develop a geological understanding of the Moon's origin, the formation of its internal structure, and its subsequent history. After the Apollo 17 mission in 1972, the Moon has been visited only by unmanned spacecraft. Name and etymology. The usual English proper name for Earth's natural satellite is the Moon. The noun moon is derived from moon, which developed from moan, which is derived from Old English mona, which ultimately stems from Proto-Germanic **non*, like all Germanic language cognates. Occasionally, the name Luna is used in poetry for a personified moon, or in science fiction to distinguish it from other moons. The principal modern English adjective pertaining to the Moon is lunar, derived from the Latin luna. A less common adjective is Selenic, derived from the ancient Greek Selene, from which is derived the prefix Seleno. Both the Greek Selene and the Roman goddess Diana were alternatively called Cynthia. The names Luna, Cynthia, and Selene are reflected in terminology for lunar orbits in words such as Apollon, Pericynthian, and Selenocentric. The name Diana is connected to Di's meaning day, formation. Several mechanisms have been proposed for the Moon's formation 4.527 plus or minus 0.010 billion years ago, some 30–50 million years after the origin of the Solar System. Recent research presented by Rig Carlson indicates a slightly lower age of between 4.40 and 4.45 billion years. These mechanisms included the fission of the Moon from Earth's crust through centrifugal force, the gravitational capture of a preformed Moon, and the co-formation of Earth and the Moon together in the primordial accretion disk. These hypotheses also cannot account for the high angular momentum of the Earth-Moon system. The prevailing hypothesis today is that the Earth-Moon system formed as a result of a giant impact, where a Mars-sized body collided with the newly formed proto-Earth, blasting material into orbit around it that accreted to form the Moon. This hypothesis perhaps best explains the evidence, although not perfectly. 18 months prior to an October 1984 conference on lunar origins, Bill Hart Inman, Roger Phillips, and Jeff Taylor challenged fellow lunar scientists. You have 18 months. Go back to your Apollo data. Go back to your computer. Do whatever you have to, but make up your mind. Don't come to our conference unless you have something to say about the Moon's birth. At the 1984 conference at Kona, Hawaii, the giant impact hypothesis emerged as the most popular. Before the conference, there were partisans of the three traditional theories, plus a few people who were starting to take the giant impact seriously, and there was a huge apathetic middle who didn't think the debate would ever be resolved. Afterward, there were essentially only two groups: the giant impact camp and the agnostics. Giant impacts are thought to have been common in the early solar system. Computer simulations modeling a giant impact are consistent with measurements of the angular momentum of the Earth-Moon system and the small size of the lunar core. These simulations also show that most of the Moon came from the impactor, not from the proto-Earth. However, more recent tests suggest more of the Moon coalesced from Earth and not the impactor. Meteorites show that other inner solar system bodies such as Mars and Vesta have very different oxygen and tungsten isotopic compositions to Earth, whereas Earth and the Moon have nearly identical isotopic compositions. Post-impact mixing of the vaporized material between the forming Earth and Moon could have equalized their isotopic compositions. Although this is debated, the large amount of energy released in the giant impact event and the subsequent reaccretion of material in Earth orbit would have melted the outer shell of Earth, forming a magma ocean. The newly formed Moon would also have had its own lunar magma ocean. Estimates for its depth range from about 500 kilometers to the entire radius of the Moon. Despite its accuracy in explaining many lines of evidence, there are still some difficulties that are not fully explained by the giant impact hypothesis, most of them involving the Moon's composition. In 2001, a team at the Carnegie Institute of Washington reported the most precise measurement of the isotopic signatures of lunar rocks. To their surprise, the team found that the rocks from the Apollo program carried an isotopic signature that was identical with rocks from Earth, and were different from almost all other bodies in the solar system. Because most of the material that went into orbit to form the Moon was thought to come from Theia, this observation was unexpected. In 2007, researchers from the California Institute of Technology announced that there was less than a 1% chance that Theia and Earth had identical isotopic signatures. Published in 2012, an analysis of titanium isotopes in Apollo lunar samples showed that the Moon has the same composition as Earth, which conflicts with what is expected if the Moon formed far from Earth's orbit or from Theia. Variations on the giant impact hypothesis may explain this data. Physical characteristics. Internal structure. The Moon is a differentiated body. It has a geochemically distinct crust, mantle, and core. The Moon has a solid iron-rich inner core with a radius of 240 kilometers and a fluid outer core primarily made of liquid iron with a radius of roughly 300 km. Around the core is a partially molten boundary layer with a radius of about 500 kilometers. This structure is thought thought to have developed through the fractional crystallization of a global magma ocean shortly after the Moon's formation 4.5 billion years ago. Crystallization of this magma ocean would have created a mafic mantle from the precipitation and sinking of the minerals olivine, clinopyroxene, and orthopyroxene. After about 3/4 of the magma ocean had crystallized, lower density plagioclase minerals could form and float into a crust on top. The final liquids to crystallize would have been initially sandwiched between the crust and mantle, with a high abundance of incompatible and heat-producing elements. Consistent with this, geochemical mapping from orbit shows the crust is mostly anorthosite, and moon rock samples of the flood lavas erupted on the surface from partial melting in the mantle confirm the mafic mantle composition, which is more iron-rich than that of Earth. Geophysical techniques suggest that the crust is on average circa 50 kilometers thick. The Moon is the second-densest satellite in the Solar System after Io. However, the inner core of the Moon is small, with a radius of about 350 kilometers, around 20% of the radius of the Moon. Its composition is not well constrained, but it is probably metallic iron alloyed with a small amount of sulfur and nickel. Analyses of the Moon's time-variable rotation indicate that it is at least partly molten. Surface geology. The topography of the Moon has been measured with laser altimetry and stereo image analysis. The most visible topographic feature is the giant far-side South Pole Aitken Basin, some 2,240 kilometers in diameter, the largest crater on the Moon and the second largest confirmed impact crater in the Solar System. At 13 kilometers deep, its floor is the lowest point on the surface of the Moon. The highest elevations on the surface of the Moon are located directly to the northeast, and it has been suggested that this area might have been thickened by the oblique formation impact of the South Pole Aitken Basin. Other large impact basins, such as Imbrium, Serenitatis, Crisium, Smythe, and Oriental, also possess regionally low elevations and elevated rims. The lunar far side is on average about 1.9 kilometers higher than the near side. Volcanic features. The dark and relatively featureless lunar plains that can clearly be seen with the naked eye are called Maria, because they were believed by ancient astronomers to be filled with water. They are now known to be vast solidified pools of ancient basaltic lava. Although similar to terrestrial basalts, lunar basalts have more wine and no minerals altered by water. The majority of these lavas erupted or flowed into the depressions associated with impact basins. Several geologic provinces containing shield volcanoes and volcanic domes are found within the near-side Maria. Almost all Maria are on the near side of the Moon, covering 31% of the surface on the near side, compared with a few scattered patches on the far side covering only 2%. This is thought to be due to a concentration of heat-producing elements under the crust on the near side, seen on geochemical maps obtained by a lunar prospector's gamma-ray spectrometer, which would have caused the underlying mantle to heat up, partially melt, rise to the surface and erupt. Most of the Moon's mare basalts erupted during the Imbrian period, 3.0–3.5 billion years ago, although some radiometrically dated samples are as old as 4.2 billion years. Until recently, the youngest eruptions, dated by crater counting, appear to have been only 1.2 billion years ago. In 2006, a study of Ina, a tiny depression in Lacus Felicitatis, found jagged, relatively dust-free features that due to the lack of erosion by infalling debris, appeared to be only 2 million years old. Moonquakes and releases of gas also indicate some continued lunar activity. In 2014, NASA announced widespread evidence of young lunar volcanism at 70 irregular mare patches identified by the Lunar Reconnaissance Orbiter, some less than 50 million years old. This raises the possibility of a much warmer lunar mantle than previously believed, at least on the near side where the deep crust is substantially warmer due to the greater concentration of radioactive elements. Just prior to this, evidence has been presented for 2–10 million years younger basaltic volcanism inside Lowell Crater, Oriental Basin, located in the transition zone between the near and far sides of the Moon. An initially hotter mantle and/or local enrichment of heat-producing elements in the mantle could be responsible for prolonged activities also on the far side in the Oriental Basin. The lighter-colored regions of the Moon are called terrae, or more commonly highlands, because they are higher than most maria. They have been radiometrically dated to having formed 4.4 billion years ago, and may represent plagioclase cumulates of the lunar magma ocean. In contrast to Earth, no major lunar mountains are believed to have formed as a result of tectonic events. The concentration of maria on the near side likely reflects the substantially thicker crust of the highlands of the far side, which may have formed in a slow-velocity impact of a second moon of Earth a few tens of millions of years after the formation. Impact craters. The other major geologic process that has affected the Moon's surface is impact cratering, with craters formed when asteroids and comets collide with the lunar surface. There are estimated to be roughly 300,000 craters wider than 1 kilometer on the Moon's near side alone. Some of these are named for scholars, scientists, artists and explorers. The lunar geologic time scale is based on the most prominent impact events, including Nectaris, Embrium, and Oriental structures characterized by multiple rings of uplifted material, typically hundreds to thousands of kilometers in diameter and associated with a broad apron of ejected deposits that form a regional stratigraphic horizon. The lack of an atmosphere, weather and recent geological processes mean that many of these craters are well preserved. Although only a few multi-ring basins have been definitively dated, they are useful for assigning relative ages. Because impact craters accumulate at a nearly constant rate, counting the number of craters per unit area can be used to estimate the age of the surface. The radiometric ages of impact melted rocks collected during the Apollo missions cluster between 3.8 and 4.1 billion years old. This has been used to propose a late heavy bombardment of impacts. Blanketed on top of the Moon's crust is a highly comminuted and impact garden surface layer called regolith, formed by impact processes. The finer regolith, the lunar soil of silicon dioxide glass, has a texture resembling snow and a scent resembling spent gunpowder. The regolith of older surfaces is generally thicker than for younger surfaces. It varies in thickness from 10 to 20 kilometers in the highlands and 3 to 5 kilometers in the maria. Beneath the finely comminuted regolith layer is the megaregolith, a layer of highly fractured bedrock many kilometers thick. Lunar swells. Lunar swells are enigmatic features found across the Moon's surface, which are characterized by having a high albedo, appearing optically immature, and having a sinuous shape. The curvilinear shape is often accentuated by low albedo regions that wind between the bright swells. Presence of water. Liquid water cannot persist on the lunar surface. When exposed to solar radiation, water quickly decomposes through process known as photodissociation and is lost to space. However, since the 1960s, scientists have hypothesized hypothesized that water ice may be deposited by impacting comets or possibly produced by the reaction of oxygen-rich lunar rocks and hydrogen from solar wind, leaving traces of water which could possibly survive in cold, permanently shadowed craters at either pole on the Moon. Computer simulations suggest that up to 14,000 square kilometers of the surface may be in permanent shadow. The presence of usable quantities of water on the Moon is an important factor in rendering lunar habitation as a cost-effective plan. The alternative of transporting water from Earth would be prohibitively expensive. In years since, signatures of water have been found to exist on the lunar surface. In 1994, the B-static radar experiment located on the Clementine spacecraft indicated the existence of small, frozen pockets of water close to the surface. However, later radar observations by Arecibo suggest these findings may rather be rocks ejected from young impact craters. In 1998, the neutron spectrometer located on the Lunar Prospector spacecraft indicated that high concentrations of hydrogen are present in the first meter of depth in the regolith near the polar regions. In 2008, an analysis of volcanic lava beads brought back to Earth aboard Apollo 15 showed small amounts of water to exist in the interior of the beads. The 2008 Chandrayaan-1 spacecraft has since confirmed the existence of surface water ice using the onboard Moon mineralogy mapper. The spectrometer observed absorption lines common to hydroxyl in reflected sunlight, providing evidence of large quantities of water ice on the lunar surface. The spacecraft showed that concentrations may possibly be as high as 1,000 ppm. In 2009, LCROSS sent a 2,300 kg impactor into a permanently shadowed polar crater, and detected at least 100 kg of water in a plume of ejected material. Another examination of the LCROSS data showed the amount of detected water to be closer to 155 plus or minus 12 kilograms. In May 2011, Eric Howry et al. Reported 6151410 ppm water in melt inclusions in lunar samples 74,220. The famous high titanium orange glass soil of volcanic origin collected during the Apollo 17 mission in 1972. The inclusions were formed during explosive eruptions on the Moon approximately 3.7 billion years ago. This concentration is comparable with that of magma in Earth's upper mantle, although of considerable selenological interest. Howry's announcement affords little comfort to would-be lunar colonists. The sample originated many kilometers below the surface, and the inclusions are so difficult to access that it took 39 years to find them with a state-of-the-art ion microprobe instrument. Gravitational field. The gravitational field of the Moon has been measured through tracking the Doppler shift of radio signals emitted by orbiting spacecraft. The main lunar gravity features are mascons, large positive gravitational anomalies associated with some of the giant impact basins, partly caused by the dense mare basaltic lava flows that fill these basins. These anomalies greatly influence the orbit of spacecraft about the Moon. There are some puzzles. Lava flows by themselves cannot explain all of the gravitational signature, and some mascons exist that are not linked to mere volcanism. Magnetic field. The Moon has an external magnetic field of about 1 to 100 nanoteslus, less than 1/100th that of Earth. It does not currently have a global dipolar magnetic field and only has crustal magnetization, probably acquired early in in lunar history when a dynamo was still operating. Alternatively, some of the remnant magnetization may be from transient magnetic fields generated during large impact events, through the expansion of an impact-generated plasma cloud in the presence of an ambient magnetic field. This is supported by the apparent location of the largest crustal magnetizations near the antipodes of the giant impact basins. Atmosphere. The Moon has an atmosphere so tenuous as to be nearly vacuum, with a total mass of less than 10 metric tons. The surface pressure of this small mass is around 3 times 10⁻15 atmospheres. It varies with the lunar day. Its sources include outgassing and sputtering, the release of atoms from the bombardment of lunar soil by solar wind ions. Elements that have been detected include sodium and potassium, produced by sputtering, which are also found in the atmospheres of Mercury and Io, helium-4 and neon from the solar wind, and argon-40, radon-222, and polonium-210, outgassed after the creation by radioactive decay within the crust and mantle. The absence of such neutral species as oxygen, nitrogen, carbon, hydrogen and magnesium, which are present in the regolith, is not understood. Water vapor has been detected by Chandrayaan-1 and found to vary with latitude, with a maximum at tilde 60 to 70 degrees. It is possibly generated from the sublimation of water ice in the regolith. These gases can either return into the regolith due to the Moon's gravity or be lost to space, either through solar radiation pressure or, if they are ionized, by being swept away by the solar wind's magnetic field. Dust. A permanent asymmetric moon dust cloud exists around the Moon, created by small particles from comets. Estimates of 5 tons of comet particles strike the Moon's surface each 24 hours. The particles strike the Moon's surface, ejecting moon dust above the Moon. The dust stays above the Moon approximately 10 minutes, taking 5 minutes to rise and 5 minutes to fall. On average, 120 kilograms of dust are present above the Moon, rising to 100 kilometers above the surface. The dust measurements were made by LADEE's Lunar Dust Experiment between 20 and 100 kilometers above the surface, during a 6-month period. LDEX detected an average of 0.3 micrometer moon dust particle each minute. Dust particle counts peaked during the Geminid, Quadrantid, Northern Taurid, and Omicron Centaurid meteor showers, when the Earth and Moon pass through comet debris. The cloud is asymmetric, more dense near the boundary between the Moon's day side and night side. Seasons. The Moon's axial tilt with respect to the ecliptic is only 1.5424 degrees, much less than the 23.44 degrees of Earth. Because of this, the Moon's solar illumination varies much less with season, and topographical details play a crucial role in seasonal effects. From images taken by Clementine in 1994, it appears that 4 mountainous regions on the rim of Peary crater at the Moon's north pole may remain illuminated for the entire lunar day, creating peaks of eternal light. No such regions exist at the South Pole. Similarly, there are places that remain in permanent shadow at the bottoms of many polar craters, and these dark craters are extremely cold. Lunar Reconnaissance Orbiter measured the lowest summer temperatures in craters at the southern pole at 35 K and just 26 K close to the winter solstice in North Polar Hermite crater. This is the coldest temperature in the solar system ever measured by a spacecraft, colder even than the surface of Pluto. Average temperatures of the Moon's surface are reported, but temperatures of different areas will vary greatly depending upon whether a spot is in sunlight or in shadow.